Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 59 and 60 in Chapter 8 in your OER textbook here. So, alright, it says something about an electric field in air of about 3 million Newton per Coulomb. It asks how far must a proton move until its velocity is 3% the speed of light. Now, the speed of light, we're going to talk about this later in the course quite a bit, but I wrote that value down here. The speed of light is about 3 times 10 to the 8th meter per second. 3% of that would be multiply that by 0.03, and you're going to get a numerical value. I'm going to let you do that. Now, this electric field, I'm going to assume it points to the right in this picture. Now, it doesn't matter what direction you put it. I can put it up, down, left, and that doesn't matter at all. I'm just picking a direction and drawing the electric field vector. We're not told much about it, but I'm going to assume that electric field is the same everywhere, meaning if I pick a point here, 3 times 10 to the 6th meter per second, here, 3 times 10 to the 6th, I'm sorry, not meter per second, Newton per Coulomb. Anyway, here, 3.3 times 10 to the 6th Newton per Coulomb, here, 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 here. We're going to assume that that electric field is the same everywhere. Now, it says something about a proton. Let's put a proton in our picture. A proton has a certain mass. I'll call that m sub p. I'm going to let you look that up. Charge of a proton, fundamental unit of charge, 1.6 times 10 to the minus 19th coulombs. And because we have a charge in an electric field, we're going to get a force on that proton, and that force will be this way. Now, it's very important to know, to realize, the electric field is not a force. It creates force, but it itself is not a force. Right? This is an actual force vector like you would put in a free body, and this force is coming from this electric field, and it's calculated by taking charge times electric field strength. This is coming right from the definition of the electric field. Remember, the electric field magnitude is defined as force per unit charge. Now, because of this force, this proton is going to accelerate. So I might kind of show that with a motion diagram. So here's kind of like snapshots in time, where the dots representing the proton. Between pictures 1 and 2 here, at this point, some time will have gone by. I'm going to call that delta t. It will have moved some distance here. I guess I'll just call that d or delta x. It doesn't matter which. At this instant, the proton is moving this way with some velocity, which we're going to set equal to whatever this product is. So this is all just pictures so far. Now, what type of equations do we write? Well, there's really 2 different ways we can work this. We can either use Newton's laws and analyze the motion, or we can use principles of work and energy. And I'm going to talk about both. Let's talk about like Newton's laws. Newton's second law, what I always call Newton 2. Remember Newton's second law, net force is equal to mass times acceleration. If this is the only force acting on that proton, right, we'd have a value for this, and then we would have a mass, because we're going to look that up, which is going to allow us to find the acceleration. Now, you're going to get a really big number for the acceleration. Don't be surprised if you get, like 10 to the 15th or something meter per second squared. Then we could sketch a velocity graph for that proton, keeping in mind that if it starts from rest, right, if I call this t equals 0, that first point would be here. Then sometime later that we don't know, the velocity is going to be some value that we do know. So that distance on the graph, we'd be getting it from here. So that'll be a known value. If we assume constant force, that means constant acceleration, which means a linear velocity graph. You can get the acceleration from here. That's going to give you the slope of that graph. So slope is a known value. And that's equal to rise over run. That's going to be this distance, which I'll call v final, over the delta t. So in this equation here, the acceleration, which is the slope, is known. The v final is known. That'll get you the delta t. Now, I think the question didn't ask for the time, it asked for the distance. Remember back from College Physics 1. displacements can be found by taking this area bound under this velocity graph. So the distance is going to equal that area. So that'll get that done. That's method number one. I mean, it's practically done for you there, about half of it. Another way we can work this problem is by principles of work and energy. If I call this point 1 and this point 2, and I write out the work energy theorem, PE1 plus KE1 plus work equals PE2 plus KE2. Then we'll just start going through it term by term. The proton starts from rest, so the initial kinetic energy, 0. The final kinetic energy is 1/2 mv squared. 1/2 m, I'll put v2 squared. And this is given in the problem. That's what we would use this for. All right, the work term. There is only one force acting on this proton between points 1 and 2. So we can calculate the work by taking this force, which can be written charge times the electric field. I'm going to go ahead and write it force here for now, but by taking this force times this distance. And that work term would be positive because the force is in the direction of the velocity as this thing's moving from left to right. Right, equals. Now, this force has been taken into account, and there are no other forces acting in this problem. Gravity is not relevant, there's no springs, there's nothing else, so there's no reason to put any potential energy terms in either. So the work energy theorem will boil down to force times distance equals 1/2 mv squared. Remember that the force, you can calculate charge times the electric field, so that'll be a known value you look up, a value given in the problem. So either of these approaches should work to, or not should, will work to get this problem worked out. All right, so that's 59. Let's chat about 60. Get rid of all this stuff. Okay, so in 60, there's a picture. There's an object, and it seems to be kind of swung out from kind of equilibrium here at some sort of angle given in the problem, 8 degrees. I'm just going to call that theta for now. Now I've kind of exaggerated the angle, but that's perfectly fine. The reason this thing is not vertical is because this thing is charged. And you'll see a bunch of lines in the problem that are representing electric field lines. And at this point in the class, at least in my college physics class, we haven't talked about electric field lines quite yet. We will very, very shortly. But basically those lines mean that there's an electric field vector pointing this way. And there's multiple lines. That means that whatever this electric field vector is, it's the same here, 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 all through this, right? Those uniform lines you see in the problem are saying there's an electric field to the right, and it's uniform. The uniform part's coming from the fact that the lines in the picture are uniform. And again, we'll talk more about that later. Because there's an electric field, and this is charged, that's creating a force on this particle in this direction. And that force is equal to the charge of this object times the electric field strength. Now, other forces acting on this object. Well, there's a string or a rope attached to it. That's going to create a force that we would typically call maybe a tension that's acting in this direction. And this thing has some sort of reasonable mass. So there's a gravitational force that acts down. I'll just go right through that charge. Right, mg. Now let's talk about this force vector right here. In physics 2, most of the time we're talking about protons, electrons, atoms, things that have really small masses. You know, proton masses are around 10 to the minus 27th. Electron masses are around 10 to the minus 30th kilograms. This object isn't a proton. This is an actual, object with a 5-gram mass. That's a reasonably, that's an actual mass that needs to be considered in this problem. So that's why we have a gravitational force in this picture. Whereas if this were a problem about a proton or something like that, we normally would ignore gravitational forces. Now, I'm pretty sure in this problem that this object is static, which means the net force is 0. So what you're going to do here, we're going to take that 8-degree angle. I'm going to go ahead and move it over to this picture. That's going to make this angle theta here 8 degrees. You could also use this angle. It doesn't matter which. This vector can be broken into components. Maybe one this way and one this way. Right, so if I call this hypotenuse T for tension, this component is adjacent to theta, so it's equal to T cosine theta. This component is opposite theta, so it's equal to T sine theta. And this is an equilibrium problem. This thing's not going anywhere. And that means the net force is 0. You can write two equations. One, sum of all forces in the y direction is equal to 0. Write another equation, sum of all forces x direction equals 0. And again, the equals 0 part is because this thing's not accelerating, no acceleration. And by the time you get these two equations written out, you should be able to solve for whatever they're asking for. So I'm sure that video will get you rolling on 60. Have a great day.